All right, so now that we know what redox reactions are and how they differ from precipitation reactions and acid-base reactions, we're going to learn how we can balance redox reactions. Redox reactions that you've studied previously would be your combustion reactions, your simple synthesis, your simple decomposition, as well as your single replacement reactions. When we are balancing redox reactions, especially when they get more complex, it definitely helps to make sure that we separate the oxidation half reaction from the reduction half reaction. We need to make sure the reactions are balanced not only for elements but also for charge. And sometimes you will have equations that don't look like they're going to balance because one side might have hydrogens on it and the other side might have hydroxides or oxygens. And you don't have it for the other half reaction. So how are you going to make it balance? Well, in acidic solution, you can always balance hydrogens with hydrogen ions, and you can balance oxygen with water. We do the same thing with basic. We just have to convert all of the remaining hydrogen ions once we have a balanced equation into hydroxides at the end to neutralize that extra hydrogen ions. So we're going to go through and do some examples. I think there's going to be 6 of them so that you'll get a chance to see this firsthand and hopefully feel more comfortable with it by the time we're done. All right, sorry, took a while to click. So we're going to balance this first reaction. This is an example of a single replacement redox reaction where we have lithium turning into lithium ions and iron 3 ions turning into iron metal. So when I'm splitting these into 2 half reactions, I'm going to split lithium apart from iron. And I want to make sure the atoms are balanced. I have 1 lithium on both sides. I have 1 iron atom on both sides, so we're good to go. But I'm not balanced by charge. So if I look at that first half equation, I can only balance by charge by adding negative electrons. So I add them to the side that's more positive. So in the lithium half reaction, I would need to add 1 electron to the product side to balance out the lithium positive ion that formed. For the iron 3 half reaction, I would need to add 3 electrons to the reactant side to balance out the charge of iron 3 with the iron atom formed on the product side. Again, with redox, you should always have something losing electrons and something gaining, which is what we see happening here. Lithium is being oxidized, iron 3 is being reduced. But when you're oxidized and when you are reduced, you need to have the same number of electrons being transferred. So to make that happen, we're going to multiply the entire lithium half reaction by 3. That's going to give me 3 lithium atoms forming 3 lithium ions and 3 electrons that are given off. And when I combine that with the iron 3 half reaction, I see that because I had 3 electrons on the product side and 3 electrons on the reactant side, they balance each other out, they cancel. And you should never have electrons shown in your final balanced equation. So at this point, because I have my electrons balanced, I have my atoms balanced, I just combine the reactant side on both half reaction, and I combine the 2 product sides on both half reactions to get my overall balanced equation. I have a total charge of +3 on the reactant side and on the product side. I have 3 lithiums and 1 iron on each side of the equation. So here's another example of a single replacement. Again, we want to separate the elements that look alike. So aluminum ions are going to go off with aluminum. Magnesium is going to go off with magnesium ions. To balance out my atoms, I have 1 aluminum on each side, 1 magnesium. I need to make sure my electrons are balanced. I have to add electrons to the side that's more positive. So I would add 3 electrons to the aluminum 3 plus side, my reactants, and I would add 2 electrons to the magnesium 2 plus side, my product side of that half reaction. In this particular example, I don't have a really easy way to make the number of electrons be balanced. So I'm going to have to find a common factor that both 3 and 2 have in common, which would be 6. So I would multiply the reduction half equation by 2 and the oxidation half equation by 3. At that point, when I distribute the 2's and 3's through, I have 6 electrons on both sides of the equation. And now I can combine my reactants and combine my products. And when that is done, I should have the same number of aluminums, which I do, the same number of magnesiums, which I do, and the same overall charge +6 on both sides of the equation. So how do we balance when we're in acidic solution? We're going to follow the same rules we saw with the more simple redox reactions. So you're going to take the two ions that contain manganese and put them together, and the two ions that contain iron and put them together. First thing you always want to do is make sure your atoms are balanced. In the first half reaction, we have 1 Mn on both sides of the equation, but we have 4 O's on the reactants. Remember I said that you balance O's with water, so we're going to add 4 waters on the product side to get the same number of O's on both sides of the equation. That gives me additional hydrogens. Because this is an acidic solution, I can easily take care of that by adding on 8 hydrogens to my reactant side. At this point, since my atoms are balanced, I just need to take a look at my overall charge. I have 8 plus hydrogen ions and 1 negative MnO4 minus ion, so that gives me an overall oxidation state of +7 on the reactant side, and I have a +2 manganese ion on the product side. So my more positive side is the reactant side. It differs by 5 with the product side, so I would need to add 5 electrons to balance out that oxidation state. My second half reaction is going to be a little easier to balance out. The more positive ion is on the product side. It differs by 1, so I would add 1 electron to the iron 3+. I have an oxidation occurring with the iron 2+. I have a reduction occurring with the MnO4-. To get the electrons to be balanced between the two half reactions, I need to multiply the bottom half reaction, the one with iron 2+, by 5. And once I have done that, I now have 5 electrons on the reactant side as well as on the product side, and I should be able to combine my 2 sets of reactants and my 2 sets of products. And if I go through and look at the overall equation, I have the same number of atoms of all the elements present on both sides of the equation. My overall charge on the reactant side is 17, if I've done my math right, and my overall charge on the product side is also 17. So this is a fully balanced redox reaction. So we're halfway through. We got 3 more to go. Again, you want to put elements that are similar together for their given half reactions. So the dichromate ion is going to go with chromium 3+. Ethanol with carbon is going to go with the CO2, which also has carbon. First thing I want to do is balance my atoms. So if I look at that first half reaction, I have 2 chromiums on the reactant side, so I need to have 2 chromiums on the product side. I'm also going to need some oxygens. Specifically, I think I'm going to need 7 on the reactant side, 7 on the product side. And that means I'm going to need to balance out hydrogens. I have 14 now on the product side, so I need 14 hydrogen ions on the reactant side. Overall, on the reactant side of that first half reaction, I have an oxidation state of +12. I have an oxidation state of +6 on the product side, so I would need 6 electrons on the reactant side of my equation to have it be fully balanced as a half reaction. With ethanol, I'm going to need to balance the carbons by putting a 2 in front of CO2. I have 4 O's now on the product side, and I have 1 O on the reactant side, so I'm going to need to add some waters to my reactant side. I always wait to do hydrogen last because I can balance hydrogen very simply, whereas when I balance O, I'm going to have to bring in more hydrogens to my half reactions. At this point now, I have 6 H's in the C2H5OH, and I have 6 H's in the 3 H2O's. So that means I need 12 hydrogens on the product side of that second half reaction. The hydrogen ions are the only part of this particular reaction that has an oxidation state of over 0 in terms of the individual molecules. So I would need 12 electrons on my product side. And inadvertently, apparently I double clicked because you now see that I needed to get 6 electrons and 12 electrons to be balanced. And it's a really easy way to do that by multiplying the top half reaction by 2. So that now gives me my 12 electrons, my 28 hydrogen ions, my 2 dichromate ions, making 4 chromium 3+ ions and 14 waters. The second half reaction is balanced but did not require any additional changes. There are 12 electrons on the reactant side as well as on the product side, so those cancel out. And I can also do that with other like terms. So if I look at this particular half reactions, I can see that I have hydrogen ions on both sides and I have water molecules on both sides. So if I take all of those reactants and products and put them together, I can combine the like terms just like I would in math class. 28 hydrogens is more than 12 hydrogens, so those 12 hydrogens are going to come over to the reactant side, giving me a net change of 16 hydrogen ions that needed to be added to make this reaction take place. And with the water, there are more waters on the product side, so the 3 waters would cancel out 3 of the 14 waters on the product side, giving me a total of 11 water molecules on my product side of my equation. And then I can rewrite the equation to show just what actually changed, the net changes that occurred. And if I take a look, I will see that I have 22 hydrogens on both sides of the equation. I have 4 chromiums on both sides. I have 15 oxygens on both sides. I have an overall charge of 12 plus on both sides of the equation. So you can always double check your work to make sure it's fully balanced. So we've done neutral and we've done acidic. Now we're going to look at 2 with basic. So in this particular example, we have 3 reactants, Ag and Cn minus cyanide ions reacting with oxygen to make AgCN2 minus in basic solution. Since the product contained both Ag and Cn, that's going to act as one of my half reactions, and O2, which doesn't appear to have anything to combine with it, is going to act as my other half reaction. We'll come back to O2. I promise it's going to work itself out. To balance out the atoms on the first half reaction, I would need 2 cyanide ions, and that's going to cause there to be a difference in oxidation state. The left side will have an oxidation state of -2, the right side of -1. So I would need to add 1 electron to my product side of my equation. How the heck are you going to create a second redox reaction when you only had 1 product? Remember, you can always balance O with water. So if I add 2 waters to my product side, I now have the same number of oxygens on both sides of the equation, and I can take care of the hydrogens that I added with water by adding 4 hydrogen ions to my reactant side. The hydrogen ions happen to be the only part of this reaction that has an oxidation state, so to balance out the electrons on both sides, I would need to add 4 electrons on the reactant side of that last equation. I have 1 electron being released by Ag and Cn minus, and I have 4 electrons being gained by the hydrogen ions and oxygen. So I would need to multiply my first half reaction by 4 so that the electrons stay balanced. I don't know why those are yellow, sorry about that. And so if I look at this particular equation now, I have 4 Ags and 8 Cn minus making 4 H pluses and O2. All those combine together to make 4 AgCN2 minuses and 2 H2Os. And I don't care if you write the AQs or the S's or the L's or the G's. Sorry, I didn't say that sooner. This is a basic solution. If you go through and check, you're going to see that you have the same number of each element on both sides of the equation and that you have the same overall charge. So this technically is a balanced redox reaction. What makes this not completely correct is that you need to have it in basic solution and you only have hydrogen ions present. Well, we can neutralize those hydrogen ions with hydroxide. And once we add that to the left side of the equation to balance out the hydrogens, we need to also add it to the right side to keep this equation balanced. The 4H pluses and the 4OH minuses make 4 waters. And so the right side did not change after it added on the 4 hydroxide ions. I can simplify this equation one more time by taking care of the fact that there are 4 waters on the reactant side and 2 waters on the product side. Those 2 waters cancel out, bringing the water count down on the reactant side to 2. So my overall equation would have the 4 Ags and the 8 cyanide ions combining with 2 water molecules as well as oxygen to make 4 AgCN2 minus ions and 4 hydroxide ions. Hydroxide being basic is going to take care of the fact that this is in basic solution. And if we go back and double check, same number of silvers, carbons, nitrogens, hydrogens, and oxygens on both sides of the equation, as well as the same overall charge, -8. All right, so this is the final redox balancing equation example we're going to do. You'll notice in this particular one it's also in basic solution, but that you actually already have basic ions present on the product side with the AlOH4 minus ion. So that's going to allow us to make the balancing process a little bit simpler than what we saw in the previous example. The two half reactions are going to be the ones with aluminum and the ones with manganese. And normally I would balance in that first half reaction, since I have equal numbers of aluminum atoms on both sides, I would balance the oxygens with water and then the extra hydrogen ions with H+. But since I know it's going to need to be in basic and I already have a basic ion present and that's the only one that's not in balance, I'm just going to go ahead and add the 4 hydroxides on. Again, I'm only doing this shortcut because literally the ion I need to balance is the one that I'm going to want in my final equation. With the second half reaction, well, before I go on to that, let me make sure the electrons are balanced. I have -4 on the reactant side and -1 on the product side, so I would need to add 3 electrons to the product side to make this equation balance fully. For my second half reaction, I'm going to balance this like we've done with acidic solution, even though I went ahead and did the first one just with hydroxide. The reason I don't balance basics straight out as base is there's a little bit more guesswork involved, whereas the acidic ones will work for you every time. And it's not such a big deal at the end to switch them over. I have 1 manganese on both sides. I have 4 oxygens on the left. I have 2 oxygens on the right, so I would need 2 waters. And because that gives me hydrogens, I would need 4 hydrogens on the reactant side. The product side has an overall charge of 0, while the reactant side has 4 pluses and a minus, so an overall charge of +3. So the 3 electrons would need to be added to the reactant side. That worked out quite nicely because since I had 3 electrons in my oxidation half reaction and I had 3 electrons gained in my reduction half reaction, that part's taken care of. I can combine the two sides, and now I have a balanced equation, but I want to make it be basic, so I need to remove those hydrogen ions. And normally I remove those hydrogen ions by adding hydroxide ions, but I already have them. So I'm not going to have to add them to both sides of the equation because I already had a sufficient number of hydroxides to balance out the hydrogen ions present. That's going to result in 4 waters being made. I now can simplify my waters because I have 2 waters on the product side and 4 on the reactant side, and that's going to allow my overall water count to go down to 2 on the reactant side. So my final equation is in basic solution but doesn't have any free hydroxide ions present because they are a part of that AlOH4 minus ion that is formed on the product side.